Okay, class, next up is the size factor. So we're going to plot the size factor, k sub b, as a function of the diameter of the test specimen. We've got this rotating circular specimen of diameter d. What is the size factor? By what percentage do we have to knock down the endurance limit of a perfect specimen for our real part, which has a different diameter? Well, let's just suppose for a second that the diameter of our part is exactly the same as the diameter of a typical test specimen, and that is around 0.3. What's the size factor going to be? Where along this vertical line at 0.3 inches diameter should we draw a dot indicating what the size factor should be at that diameter? Again, it's the same as an actual specimen. Think about that for just a second, maybe pause the video if needed. It's going to be 1.0, right? Just like we saw, if we have a polished finish like the ideal specimen, Ka was 1. Well, if we have the exact same size of our typical test specimen, then Kb is equal to 1. And where does it go from there? As the diameter gets bigger, does it go up? Do we have a greater size factor? Do we get 110%, say? Or do we get less than 100% of the endurance limit of the specimen? Well, as you can probably tell from the vertical axis going all the way up to 1 but no higher, it goes down from there. So this is what the curve looks like. Shigley gives an approximation for it. The mathematical approximation looks something like this. It's piecewise defined. For diameters between 0.11 and 2 inches, we're going to follow this section of the curve, and you can see a little bit of a kink in the curve there corresponding with 2 inches. 2 inches up to 10 inches, you're going to follow a different curve. It's just piecewise defined to more accurately reflect the data. Now, why do we think that the trend is for the size factor to go down as the size increases? Think about why that might happen, right? The part gets stronger. No doubt that the part gets stronger. You've got lower stresses for a given applied load. But we've already converted to stress. We're saying that the stress to which you can subject the part gets lower. The endurance limit of the part is smaller. Why might that be? Before I give the answer, think about where fatigue comes from. Think about the fact that for a polished mirror finish, we didn't have any cracks on the surface, right? And so we had a Ka of 1. As we had a rougher surface finish, we could have cracks on the surface, micro cracks that could grow bigger, and we ended up with a Ka that was smaller than 1. What about the size of the part might affect fatigue then? It's not explicitly explained in Shigley, but it seems to me that if you have a larger part, then there's just more area over which you could have these cracks. There's a greater chance that you could have cracks. So the larger the part, the more cracks there are to begin with, and the lower your endurance limit is going to be as a result. So this is all for bending and torsional type loads. It turns out for an axial load, pure axial load of a cylindrical part, Kb is equal to 1. Your size doesn't matter. But what if your part isn't circular? If your part isn't circular, and actually if it's not in a rotating beam test, what do? These values, this equation here, is only valid for a rotating bending beam test, type test. So what if your part is not a rotating cylinder subjected to bending? What we're going to do is we're going to say, for our given part, let's convert it to an equivalent cylinder, a rotating cylinder, calculate the diameter of that cylinder, and from that diameter we can get the Kb. And this all has to do with the area of the cross-section that gets stressed highly, right? That's what size did. The greater the size, the more area which could have these cracks the part has, and so the lower the endurance limit. So what we're going to do is look at the 95% stress area of the part. If we have a rotating circular specimen, then at the very outside edge, that's going to see the maximum stress. At a radius of 0.95 times r, this part of the circle is going to see 95% of the maximum stress. And this area in between those two, these are all the points in the cross-section that are subjected to a stress that is 95% or above of the maximum stress seen in the material. This is the 95% stress area for a rotating cylindrical cross-section. So that's the 95% stress area for a cylinder, a rotating cylinder. But we want to calculate the 95% stress area first of our shape's cross-section. So let's say we have a rectangular beam and we're bending about the neutral axis, which is a horizontal line here. Which part of this beam is subjected to up to 95% or above the maximum stress? We know that the very top and the very bottom are where the maximum stresses occur. What portion of this rectangular cross-section is stressed at 95% or above that? The stress increases linearly with the distance from the neutral axis. So this shaded region is 95% out to the outermost fibers of the beam towards the top and 95% of the way towards the outermost fibers of the beam on the bottom. This shaded region is the 95% stress area of a non-rotating rectangular cross-section. What we're going to do then, let's say that this is our actual case. We're going to say, what would the size of a rotating cylinder be with the same 95% stress area? Because we can expect that our endurance limit is kind of proportional to that area where there could be these cracks that could develop, right? We're going to calculate the equivalent diameter of a rotating cylinder that has the same 95% stress area. We're going to take our rectangular cross-section, which has this as its 95% stress area, and we're going to convert it into a rotating cylinder, which has this as its 95% stress area. And we're going to find the radius of that. We're going to take a rotating cylinder with the same 95% stress area. We're going to use the radius or the diameter of that in order to calculate the size factor. And there's formulas for that. We've got formulas for different kinds of non-rotating cross-sections, how to calculate the equivalent diameter that we're interested in. Let's see that with an example. We've got a polished steel specimen. It is cylindrical. It has a diameter 2 inches and ultimate tensile strength 200 KSI, and it undergoes a fatigue test. Estimate the endurance limit when we have a typical rotational bending test, and also when we have a non-rotating bending test, when the load itself varies sinusoidally. Here we've copied some relevant information from the book. So this will really help us for the first part. The second part, we have 95% areas and equivalent diameters for non-rotating structural shapes. So this is how it works. We're trying to find KB when our part has a diameter, D is equal to 2 inches. So KB, we just need to follow one of these formulas here. Because our part happens to be 2 inches, which is where these two curves meet, we can use either one. So I'll try both of them just so you can see that both of them meet up in the center. So we've got 0.879 times 2 to the negative 0.107. And that is 0.8162. We could also calculate it as, let's use this formula, 0.91 times d to the negative 0.157. And we get the same thing, 0.8162. So if your diameter of a rotating beam specimen is greater than 2 inches, you're going to use this equation. If it's less than 2 inches, you're going to use this one up here. Now, what if your diameter was 0.11? Let's just think for a second. If our diameter is smaller than the typical test specimen, which is 0.3 inches, if it's smaller, what do we expect KB to be? Is it going to be equal to 1, less than 1, greater than 1? Let's plug it in. If our diameter happened to be 0.11, then we would use 0.879 times 0.11 to the negative 0.107. That's actually higher than 1.113, because we have less of an area that's subjected to the high stresses, less area that could have cracks in it that could propagate and cause fatigue failure. So it's possible to have K factors, Marin factors, that are greater than 1 in some cases. So if our part has a smaller diameter than 0.3 and it's subject to rotating bending loads, then we might have a KB that is greater than 1. But that's not our real situation here. This here was for the rotating cylinder. It's when we had, here's our test specimen, and we had this 4-point bending sort of applied to the cylinder, puts this in a constant bending moment. And so if our material point is at the very top while it's rotating, then it's going to be in compression. If as it rotates, it moves down to the bottom, now it's going to be in tension, and it's going to sinusoidally vary in between. Now let's think about if it's a non-rotating cylinder, and it's actually these forces. Let's say that these forces were some varying sinusoidally, where omega is the rotational speed. So that means that a part that's at the very top here, it's still going to see sinusoidally varying stresses. But this point right here, in a rotating specimen, it would have been subject at some point in time to the tensile stresses, and at some point of time it would have moved up here and seen compressive stresses. But in this non-rotating example, it's always right on the neutral axis. That point is never going to see any stress at all from this bending. So we have less of an area that actually sees these stresses. And so we need to convert from a non-rotating shape. We need to find the 95% stress area and find the equivalent diameter of a rotating cylinder with the same 95% stress area. It turns out there's a formula for that. All we need to do is use this formula. The equivalent diameter that we're interested in is 0.370 times the diameter of our actual part. 0.37 times 2 inches. 0.74 inches. We're going to plug that into our expression for KB. So the KB in the non-rotating case, because there's less of an area that has these high stresses and that could cause fatigue failure, 0.879 times 0.74 to the power of negative 0.107. And so here we have 0.908 is our KB. It's better than in the rotating case. So if we had a rotating cylinder that was 2 inches in diameter, then we would expect to get 80% of the endurance limit that we would have in a rotating beam test with diameter 0.3 inches. If we have a non-rotating cylinder and it's actually the forces that are applied that vary sinusoidally, then we'd only have a 10% reduction of the endurance limit that we'd get in a rotating cylinder test.